there's something that's probably a little familiar about this. We all have limits, yes? But of course, I think this is obvious, the limits used in math, well, hey, if we have limits, usually it's one-sided. For example, oh, what's the maximum temperature that an organism can tolerate? Or what's the minimum temperature it can tolerate? Well, yes, in math you have left-handed limits and you have right-handed limits, or left-sided limits, right-sided limits. Wording may vary depending on locality and therefore the diction, so choice of words. But what happens when you need to consider the limit as x approaches a in general? For example, oh, say y equals x. What's the limit of the value of y as x approaches a or b or whatever we like? Well, that requires that, okay, first of all, you can approach it from this side. And second, you can approach it from that side. And very importantly, the limit exists if both sides, well, the point you're approaching converges to the same value. This is not like, say, oh, a rational function. No, that doesn't work. And of course, say, oh, hey, let's take log of x and let's make x approach 0. You have a one-sided limit. Do you have a two-sided limit for x approaches 0 for log of x? No, you don't. So, please be careful that sometimes this is the way we write limits in, well, pen and pencil, or whatever writing implement you prefer, and paper, or blackboards. But in computer software, some types of computer software, when you take this and add text after it that's not in the formula box, it immediately decides that it should be written as a subscript instead, which is not quite the way it's supposed to work. Now, what does it actually look like when the software doesn't cooperate? Generally, something that looks like this. And this corresponds to f of x. So, the x approaches a from the negative side is called a left-hand or left-sided limit, whereas the right-hand side is, well, okay, as we well know, number lines have positive generally on the right-hand side or up. Now, not necessarily always, but at least the horizontal axis is usually pretty steady. Why? Oh, hey, sometimes, say we're plotting how far an object has fallen. Oh, positive distance fallen. Okay, I mean, usually we use up as positive. But, well, mileage may vary. Be careful. Okay, so here we have an example that's, well, what does this simplify to? We can see that x squared minus 1 over x minus 1 is equal to x plus 1 x minus 1 over x minus 1. So, how can we cancel this? Well, we can if we put in a caveat, which is that x is unequal to 1. And lo and behold, we have a straight line. The slope is 1. the y-intercept is 1. Okay, x is unequal to 1. Yep. Now what? Well, we can see that this is discontinuous. Because, hey, we have the limit on either side is the same. But there's no value there. There's a hole in this function. So it's a discontinuity. Now what can we say? We can say that limit as x approaches 1, because it specifies the number, from the negative side of f of x is equal to, well, going from that side, as the value of x grows infinitely close to 1, we get 2. Or infinitely close to 2. So 2. And the limit as x approaches 1 from the positive direction of f of x is, well, it's also 2, as we can see here. And then what? Hey, what's the value of f of 1? It doesn't exist. But what does exist? Lim x approaches 1 of f of x is equal to 2, because these two get put together to make the lim of x approaches 1 in general. And, well, not exist. Or, what else can we write for it? Okay, what's 1 squared minus 1? 0. And 1 minus 1 is 0. So it's 0 divided by 0, which is more technically speaking, it should probably be written as f of 1 is indeterminate. However, usually does not exist is the answer they expect. Indeterminate is correct, but since we haven't even got into imaginary numbers really, well, they don't expect that much detail, usually. Mileage may vary, so be careful. Okay, example 2. Now suppose we define a value for x equals 1, and what happens? Well, what does g of x here approach? We can see that this line still approaches the point 1, 2 from both sides. 1, 2, as in x equals 1, y equals 2. But what's the actual value there? Okay, it's defined as 3, fine. Hey, does that actually make a difference? No. We can clearly see that the lim x approaches 1 from the negative side of g of x is equal to 2 is equal to lim x approaches 1 from the positive side of g of x, and therefore is equal to lim x approaches 1 in general of g of x. So, the limits, you can tell me that, oh, let's punch a hole in this curve and let's move the value at that single x value somewhere else, up or down or wherever. Well, actually, not wherever. Why? Because if you move it sideways, it's for another x value, and you wouldn't have a function anymore if you have more than one range value for a domain value. Therefore, you can slide this up or down Okay, what does that do to the limit? Oh, as you approach infinitely closely, remember that a curve is not in fact a collection of points, unless you want to be really, really technical on what the idea of a point is. Why? I mean, yes, on your graphing calculator, you can scan between pixels. Fine. But wait a second. What about all the values between those pixels that are displayed? Like say, oh, x equals 0.1, x equals 0.2. Hey, what about everything in between? Like say, x equals 0.15. So every single point, every single discontinuity that is a point discontinuity, well, they take up 0 space on the x-axis. This doesn't sound like very much, probably, but when we get to probability distributions and talk about how, oh, under this whole curve of probabilities, there is an area of 1, i.e., something must happen in all cases. 0 is impossible, 1 is certainty. So under this whole area, there is an area of 1. Okay, what's so weird about that? Guys, under any given outcome, there is an area of 0. Because it's going to be a line. If you get a very large number of males or of females and say that, oh, their height is just distributed along a normal curve and we're using this normal curve to approximate it. Okay then guys, what's the probability that any one person in this very large crowd has a height that is precisely some value? The probability is 0. Because of the definitions of how areas are calculated. And very soon we will see, when we talk about integrations, that the way areas are calculated has certain implications, such as the fact that any one point, draw a line, and that line has an area of 0, because it has a width of 0. Just like here, the discontinuity has a width of 0. Of course, if you say have a bigger discontinuity, well, wider, then that's something completely different. In which case, of course, you can't find the limit in the middle where there's no function to deal with. Now, another form of discontinuity for which there is no limit value is one where we say go to positive and negative infinity. But we'll get to that later. Okay, here we're going to prove that if this is true, then the function can be continuous. So a continuous function will always have this characteristic. Why? Well, hey guys, suppose we have a curve or a slope or whatever on, say, a road. We assume that there is a pothole in the road. And as we approach the pothole from one side, we get a particular value of expected height of road. Yes? And as we approach from the other side, we get another particular expected value. And okay, so if the road's perfectly smooth, then we expect the value to be the same approaching from either side. And once we actually get there and find that the value at that point is this expected value, what does that tell us? That tells us that we were wrong to expect there to be a pothole in the road. There is no pothole. So, how do we show that mathematically? Well, it looks pretty much exactly like what we were doing earlier. Approaches 1 from the negative side. We get f of x is equal to 2. And what about from the positive side? Lim as x approaches 1 from the positive side of f of x is equal to 2. And what does this tell us? This tells us that put together, limit of x approaching 1 in general for f of x is equal to 2. And what is f of 1 here? F of 1 here is clearly 2. F of 1 equals to limit of x approaching 1 of f of x. Now, as we can see, if you approach it from one side and expect it to be a particular value, and you approach from the other side and expect it to be a particular value, and you get there from both sides, expect the same value, and you find that it actually is that value, what can you say? Well, there's no gap. Limits from both sides equal to the actual value. The actual value. We ran a little mathematical example up here, and then we can explain this better actually verbally. Because there are some concepts where if you want to show this mathematically, it takes a while. And words work faster. Of course, there are plenty of concepts where the converse is true. So if a question tells you to explain, use the method you feel is more appropriate. Preferably use both to some extent. Okay. There is no discontinuity. Okay. Now, here we should point something out here. Wait a second. Just having the limit from both sides existing and being the same, and wait a second. What if we deal with, say, 1 over x squared? Well, obviously, we need to make sure that the f of x we're looking for, or f of a rather, is actually defined. And that the limits converge to that f of a. Okay, so suppose we have a few sequences. What is the limit for this sequence here? Okay, we get 1 over n. So limit as n approaches infinity of 1 over n is equal to, well, okay, we know it's equal to 0, but if we want to write a limit expression, it should look like this. Of course, depending on what we're actually doing, we might have to do some substitutions. We might also have to do some simplification, but in this case, equals 0 is enough. Fortunately, when we write this limit expression, which is really lim n to infinity 1 over n equals 0, well, when we write this is equivalent to stating the limit, which means that there's not much writing needed for the state the limit part, other than us verbally saying it, usually. Most teachers are fine with this. So there was much rejoicing. Hooray. Okay, so here, for this we have limit of n approaches infinity of 2 to the power of 1 minus n, which is equal to 2 to the power of 1 minus infinity, which is equal to 2 to the negative infinity, which is 0. Now, yes, okay, we could have gone from this straight to 0, but I wanted to make sure that we all understood that any integer plus or minus infinity is plus or minus, as the case may be, infinity. Okay, yes, there are bigger and smaller infinities, but that's a different concept we can cover later. Okay, so next, let's find for this graph below some limits. Yes, this is what happens when software is uncooperative. You will encounter this quite a bit. So please don't be too surprised if you see this, but remember that the proper format is to have this underneath the lim instead of as a subscript. All right. So for 4 from the negative side, well, it's pretty obvious it goes to negative 2. And for 4 from the positive side, it also goes to negative 2. And from both sides, well, hey, these two are equal. Therefore, that's negative 2. And what's f of 4? So the actual value at x equals 4, that is negative 2. Now let's try this for x equals negative 2. Now we're presuming, according to the problem, that the y value is an integer there. Just looking at graphs, unless the points are specifically marked out, is very hazardous business. We should generally not do it if possible. Because for all we know, this could be, y-intercept is negative 3.99 or something like that. So if they point out that it's supposed to be an integer, treat it as such. Otherwise, well, it's your plan B, so to speak. It's much better if you actually have the equation of the function to work with. But in this case, we don't. So doing a through d for x equals negative 2. Now that means the left-hand limit, the right-hand limit, or left side, right side, depending on region. So limit of x approaches negative 2 from the negative side for f of x is equal to, well, we can see that it approaches 1. And the limit as x approaches negative 2 from the positive side for f of x is equal to 1. And from both sides, well, these are equal, so from both sides we get lim x approaches negative 2 of f of x is equal to 1. And what else? Well, f of negative 2 is equal to 1. So what do these things tell us? Or more specifically, what do these 2 points here tell us? That this is continuous. The fact that f of negative 2 is defined is kind of already a given by the fact that we have a defined value for this. Continuing, in summary, a sequence is a function f of n approach, which is Tn. Wait a second. What's the difference between f of n and Tn that makes this an arrow instead of an equal mark? What about, say, n equals 3.9 or 2.5 or whatever, non-integers? Well, a sequence is really a series of points if you plot it on a grid. So what happens if we join these points with a curve that describes the full curve of the relationship that specifies the sequence? Well, we get this function f of n. The domain, yeah, okay, for a sequence, it's a set of natural numbers n. But if we were to approximate with a function, then we would get a much bigger domain. So, why is it still a function even if it isn't the expanded domain? If it isn't a smooth curve? Well, for any one domain value, there is only one range value. So for t1, that's one value. For t2, that's one value. For t3, t4, so on. Now here we mean natural numbers as in positive integers. So there's no t0 generally. Now the limit as x approaches a of f of x exists if you have these three criteria. So from the left side, when we approach it on the curve, we get a certain value that exists. So it's not in, say, oh, a gap. What's here? Well, let's try these two x values, say x1 and x2. No limits, because, well, we can't approach them. So the limit from the left-hand side has to exist. The limit from the right-hand side has to exist. And, well, these two limits have to be equal. Whether or not they are actually equal to the function value there is irrelevant. You will still have the same limit. So you can read it as this. Limit of f of x as x approaches a is equal to L. If it's equal to L. You could set it to equal to m or whatever else if you like. But if these two limits from the two sides, so left-handed, right-handed, or sometimes just left hand, right hand, no ed at the end. If they're not equal, then you don't have a limit of f of x as x approaches a. Now, if it's equal and the value you're approaching from both sides is actually equal to the value of the function there, then it's like, oh, hey guys, if we expect there to be a pothole or a big boulder in the road, if we come from this side and expect it to be a particular height, we come from that side, we expect it to be the same height, and we find that it actually is that height, then what does that tell us? Well, there's no pothole and there's no boulder. So it doesn't stick out or sink down. Why can't it say, instead of moving only up and down, why can't we move it sideways? Well, it wouldn't be a function then because, well, we can move the whole thing. So the discontinuity and the defined value sideways, but we can't just move that defined value sideways because then, well, we would have one domain value, two range values. That's not a function anymore. So here, this is what we put for the conditions for continuity. So where does this all lead us? Well, this is the end of this section, and we'll see where it leads us next section.